High in the mountains above Alamogordo is Apache Point Observatory, an installation of 4 telescopes featuring the largest non-military optical telescope in New Mexico. Apache Point Observatory, or APO, was formed in 1984 by the Astrophysical Research Consortium, ARC, initially a group of 5 universities including New Mexico State University. The ARC members shared a common problem. In order to conduct good astronomical research, you needed a large telescope, and no single university could afford one by themselves. But by grouping together and sharing time on the sky, it was possible to build a valuable research facility. The ARC 3.5-meter telescope and facilities were completed in 1987, but the primary mirror was delayed, and the site was not dedicated as operational until May 10, 1994, just in time for a rare annular solar eclipse. Since then, the site has grown to include 4 telescopes, and the observatory has been collecting astronomical data with a variety of spectrographs and imagers that detect both infrared and visible light. The Apache Point telescopes study celestial objects both seen and unseen, but the ARC 3.5 has an important difference shared by only a handful of telescopes around the world. It also emits light.
What you just saw was laser light shining through the ARC 3.5-meter telescope. This is our control room, where we conduct most of our science operations. In general, the science involves using the telescope and instruments to collect light from distant stars and galaxies. But one of our programs, the Apollo program, uses the telescope to transmit light as well. This is one of a handful of lunar laser ranging programs around the globe which use lasers to measure the distance to the moon to a very high accuracy. We shine the laser light backwards through the telescope. It travels out through Earth's atmosphere all the way to the moon. Specifically, we aim the laser at retroreflectors sitting on the surface of the moon. There are 5 such retroreflectors. 3 were left behind by Apollo astronauts during missions Apollo 11, 14, and 15. 2 are mounted on Russian robotic rovers, which have since run out of power and are just sitting in one place. As a matter of fact, out of all the science equipment left behind on the moon from various missions, those 5 retroreflectors are the only items still in active use because they don't require power. This is a type of retroreflector known as a corner cube. Imagine hitting a racquetball into the corner of the court. It comes straight back at you. Similarly, if you coat the inside of a cube with reflective material, it will shine light directly back at its source. Unlike a typical flat mirror where angle of incidence equals angle of reflection, if you tilt that flat mirror, you'll be seeing something off to the side. With a retroreflector, any light is reflected directly back to the position it came from. Each of the retroreflectors on the moon consists of multiple corner cubes laid out in a grid about the size of a laptop computer. We shine our laser at the moon in very short pulses and time how long it takes for the light to travel to the moon, be reflected, and come back to us. The moon is about 240,000 miles away. Light travels at about 186,000 miles per second, so it takes our light pulses approximately 2.5 seconds to travel to the moon and come back. By measuring that timing very accurately, we can determine the distance to the moon to an accuracy of 1 millimeter. But why? Why do we care about the distance to the moon? Well, we're actually doing these measurements 5 or 10 times a month. The moon is constantly in motion around the Earth, and that motion is controlled by gravity. What we're really trying to measure here is gravity. Einstein's theory of general relativity predicts how massive bodies should behave under the influence of gravity. We want to see if those predictions are accurate. Or is there more to the story that hasn't been told yet? Each of our laser sessions lasts about an hour, and during that time, we try to measure as many of the 5 retroreflectors as we can, because getting more points gives us more information. 2 points determines a line. 3 points determines a plane. The moon is not a plane, it's a sphere. So 4 points tells us the curvature of the sphere, orientation of the sphere. 5 points tells us how that sphere is flexing. The Earth exerts gravitational tidal forces on the moon, just as the moon exerts tidal forces on Earth. On Earth, those tidal forces cause the oceans to rise and fall. On the moon, there are no oceans, only rocks. So the tidal forces caused by the Earth cause the rocks to flex. By measuring multiple reflectors multiple times over the course of each month, we can determine how is the moon flexing, how is the moon's orientation changing, how is the moon's orbit changing. Is it following the predictions made by Einstein? Or is there something more we want to know? So, let's go look at the telescope. This cabinet is for the Apollo control electronics. Now the dome is kept unheated because we don't want a temperature difference between the telescope and the surrounding air. We want to minimize atmospheric distortions, like the kind of shimmer that you see above a hot road or a radiator. But humans in February like to be warm, so I'm bundled up, and our electronics like to be bundled up with insulation as well. This is where we keep a lot of our control electronics for the laser. The really big power supplies are in another insulated box. But here we have some of our resistors that can be adjusted, controls for our guide camera, controls for the laser, the computer that runs the laser, and power supplies for all of our detector electronics. The laser itself is mounted directly on the telescope on an optical bench, so it moves with the telescope. It also likes to be kept toasty warm and insulated. We have 2 powerful flash lamps, which produce laser light in the infrared range, which the human eye can't see. So we have plenty of other optics and electronics designed to concentrate the laser light into a little pencil beam, take that infrared light and frequency double it so that it's green and visible to the human eye. And also make sure that the laser pulses 20 times per second the way we want it to, instead of shining steadily. This pencil beam comes out of the laser light path and goes through our detector area and out to the telescope. It shines backwards through the telescope, opposite to the way the incoming starlight normally works with our other astronomical projects. The laser light, when it goes out through the telescope, it changes from a pencil beam to a wide collimated beam, 3.5 meters wide as the size of the telescope. That means it's also not dangerous to human skin or eyes, or to satellites or planes. So the laser light shines all the way to the moon and encounters retroreflectors left behind by the Apollo astronauts. The retroreflectors send the light directly back in the direction it came from, which is towards the telescope. The incoming light returning from the moon comes through the same path that starlight follows, backwards from the path of the outgoing laser light. Having the outgoing and incoming laser light follow the same path allows us to measure the timing much more accurately. The incoming light gets divided up. Some of it goes to this guider camera here, but the laser light goes down to our special detector, which is capable of detecting single photons. That's how we can detect very small numbers of photons returning from the moon and measure the distance to the moon with very high accuracy.
Every time the laser is scheduled to be used, the FAA is emailed so that they can publish a notification to area airports to avoid the observatory's airspace. At the distances the planes are at, the laser beam is diffuse enough that it would not blind pilots, but it could disrupt their night vision, and this would be a bad thing. Two spotters stand on the catwalk watching for aircraft that ignore the notice. Each has a switch that will immediately shut off the laser if a plane is seen. When the laser is running, it will stay on the same target for 5 to 10 minutes, then switch to a different retroreflector. The laser pulses 20 times a second. Each pulse emits 100 quadrillion photons. That's a 1 with 17 zeros behind it. A run is considered a success if they can get at least one photon returned per pulse.